Oh, hey, sorry, I didn't see you there. I was just finishing up studying for my chemistry test. I was wondering if you could take a little time and listen to our presentation on the hypoxia and inducible factor. So, I would like to start off the presentation by posing a question to you. This question is, in the United States, how many people do you believe will die from cancer in the year 2017? Now, based from the American Cancer Society, it's predicted that 600,290 people will die from cancer. Take this into regards, right now there are 325,178,147 people living in the United States, meaning that almost 8 out of every 4,000 people will die. Take this in the terms of students at UOW, and this is 8 out of every 4,000 undergraduate students could die of cancer in 2017. Now this is a daunting statistic, and this leads me to the whole point of the presentation on hypoxia-inducible factor. This here is a representation of the enzyme HIF1A. This enzyme has the ability to promote cell proliferation, reduce specific enzyme responses, reduce immune responses in the body such as cytotoxic T cells and T regulatory cells, while also helping the cancer cells process of metastasizing from its original location, consuming lactic acid production, increasing the promotion of vascular endothelial growth factor, or VEGF, to increase vascularization to the tumor. Now, HIF is a transcription factor that can be induced when the cell is placed into a hypoxic condition. A hypoxic condition, defined by the Pharmacology of Therapeutics, volume 164, is when oxygen supply fails to meet the demand of the cell. The cellular response to hypoxia is mainly mediated by the hypoxia-inducible factor family of transcription factors, which regulate the expression of multiple genes involved in the processes that drive the adaptation and progression of cancer cells. Therefore, tumor hypoxia and HIF affect most of the cancer hallmarks. This is including cell proliferation, apoptosis, metabolism, immune responses, genomic instability, vascularization, invasion, and metastasis. So in saying all this today, Alice and I will be discussing aspects of the enzyme at the protein level, the enzyme's location and function after post-translational modification, current research on the enzyme and its effects on tumor size and cell proliferation, and HIF1A as a biomedical marker for tumor malignancy.
So the enzyme hypoxia-inducible factor 1 alpha, or HIF1A, is a subunit of hypoxia-inducible factor 1. And HIF1 is composed of two subunits, the alpha and the beta. Both the alpha and beta subunits are comprised of a basic helix-loop-helix domain that participates in DNA binding, and two PAS domains that facilitate the heterodimerization of the two subunits, and a C-terminal transactivating domain. You can see with this picture of HIF1 bound to DNA, the two different helices that are bound to the DNA, one for the alpha subunit and one for the beta subunit. And so these helices are part of the basic helix-loop-helix domain. And then to the left, you can see a bunch of beta sheets and more helices. And the beta sheets make up the PAS domains. And so typically, they have 5-stranded anti-parallel beta sheets and several alpha helices, which can be better seen in the picture over there, with the five yellow strands and then more alpha helices. And so then the last domain that is the most variable between the HIFs is better seen between these two pictures. So this is a complex with the C-terminal transactivating domain of HIF1A with a complex, and then here is just the domain highlighted. And so it's just composed of loops and helices. And so hypoxia-inducible factor 1 is part of a hypoxia-inducible factor family, all of which have similar functions. In addition to HIF1, there's also HIF2 and HIF3. And there's not much information on HIF3, but HIF1 and HIF2 are known to have similar structures and functions. So here's a picture of HIF1 and HIF2 in comparison, both bound to DNA. So you can see that they have similar structures, but some small differences can be seen with the purple helices. And so the basic helix-loop-helix domains and the PAS domains are structurally very similar, but the last domain, the C-terminal transactivating domain, is very different, suggesting that they may have unique target genes. And so this picture here lines up the similarities and differences of the domains of HIF1A and HIF2A. You can see the first domains of the basic helix, loop helix, and the PAS domains are pretty similar, but the last domains of the C-terminal transactivating domain are not as similar.
So the research done with HIF1A starts back in the 1990s, where a popular cancer-fighting theory was proposed that we should interfere the hypoxia we should interfere with the amount of oxygen to starve tumors to death. In the 2000s, one magazine writer called this strategy the most important single insight into cancer research in the past 50 years. Well, spoiler alert, it's not even close to that, as researchers now are still at a standstill on trying to understand how we can manipulate this HIF1A enzyme to help with chemotherapy treatments as well as immunotherapy treatments. So the main issue researchers have found is they underestimated the strength as well as the resilience of the cells when deprived of oxygen. Now, low oxygen levels will launch the cancer cells into a metabolic panic, starting with the activation of HIF. From there, many processes can occur, as seen in the picture up here. So from the picture here, I would like to highlight a few things for discussion later on. First is HIF will promote a gene called VEGF, or vascular endothelial growth factor, which will then activate a MDR1 factor, which pretty much increases vascularization to the tumor. HIF has also been seen to help with cancer metastasis using collagen fibers. Unfortunately, it's not known the mechanism for how the cancer cells are able to do this, but the promoter's mechanism is through collagen fibers. Thirdly, HIF has been seen to be able to take up lactic acid. Now this is extremely important because when the cell is going through anaerobic exercises or lack of oxygen, it produces a lot of lactic acid, and if this lactic acid was just built up and stayed there, then it would increase the pH level, actually degrading the tumor. So this leads me to the mechanism with HIF alpha is in normoxic versus hypoxic conditions. So when HIF alpha undergoes normoxic conditions, it will translate from HIF alpha mRNA, and then based upon this translation, it undergoes hydroxylation at a conserved residue. This process is mediated by prolyl 4-hydroxylase, seen here, or PHD, as well as FIH1. Based from this hydroxylation, this will inhibit transcriptional activity by preventing the interaction with CBP-P300. So the degradation of HIF alpha is mediated via a ubiquitin-dependent process executed by the VHL complex, seen here through hydroxylation. After this, the HIF1A alpha, 1-alpha will degrade. Now, under hypoxic conditions, the HIF1 alpha will be able to stabilize, followed by translocation into the nucleus and a dimerization of HIF1 beta. Then it will be able to bind with other cofactors CPB-P300 and induce transcriptional factors as stated above in the previous slide, such as decreasing your immune response as well as increasing vascularization. So now I'd like to transition into the two articles that stem this whole presentation for us today. The two main articles that stemmed the idea for the presentation were the therapeutic targeting of hypoxia and hypoxia-inducible factors in cancer, as well as hypoxia-inducible factor 1A promotes primary tumor growth and tumor-initiating cell activity in breast cancer. So now within the article on hypoxia-inducible factor 1A promotes primary tumor growth and tumor-initiating cell activity in breast cancer, there was a majority of the research completed on the effects of HIF1 alpha on tumor growth, volume, and basal marker expression in culture cells within specific cell culture environments. The main research we would like to highlight today is on the deletion of the HIF1 alpha and the growth and invasion of the tumor. So we observed that HIF1 alpha expression generally increased during tumor progression in MMTV PYMT mice. This stands for mouse-mediated tumor virus. This is actually one of the main viruses that has been known to cause cancer in female mice will cause breast cancer. The observed HIF-1A wild-type and knockout cell lines were created using specific mechanisms listed in the article, but we're going to sprinkle some great Dr. Eve biochemistry magic and say that these mechanisms magically happen, and that's all we have to know. So next I want to describe how the wild-type and the knockout cell lines for HIF-1 alpha were placed into a hypoxia chambers. Again, we don't know the mechanism, they were just placed into these chambers. These chambers were at certain oxygen levels. The one to the left seen here was at 20% oxygen level, and the one to the right over there was seen at 1% oxygen level, which is the literature value for inducing hypoxia on a cell line. Next, you can see that there's wild type and knockout cell lines, but they were also placed into certain growth factors. One on the left being 5% FBS, which is fetal bovine serum, and endothelial growth factor, and one on the right for 2% FBS. The article actually didn't go into much detail on the certain differences, but they stated that having the endothelial growth factor will actually increase vascularization, even the knockout cell line, but they didn't go into the results on whether this actually happened or not. Now, based on this, you can see that the wild types for normoxic and hypoxic conditions, the wild type for normoxic condition actually had higher tumor growth of both, while in the knockout normoxic versus knockout hypoxic, again, the knockout normoxic had higher tumor growth. But comparing the hypoxic condition for wild type versus knockout, you can see a pretty big difference in the amount of tumor growth. And this is where our hypothesis came into how this happened. Within the article, there was no hypothesis as was stated. It was stated that this happened, that they had their p-value of 0.05, and that's it. But me and Allison, after talking for a while, came up with a specific hypothesis as to how this could happen. Now, as I stated before, in the 6 factors that HIF can actually influence, one of them was VEGF, or vascular endothelial growth factor. Now, what this does is it actually increases the vascularization from the tumor back into your blood, which can allow for more blood flow into the tumor, thus regulating the tumor growth and increasing cell proliferation in the tumor. So if you're able to take out the HIF, you're able to then inactivate the activation of the VEGF, which would then inactivate the MDR1 gene, thus decreasing vascularization to the tumor. Now, I just want to point out this is a hypothesis. We weren't able to find in any other research articles that this is happening, but this is what we were able to come up with between us. Now, this is for Allison. We'll talk about further research as well as what we know within cancer diagnosis.
So for today, one applicable use for HIF-1A in regards to biomedical research can be seen in oncology-based hospitals such as St. Jude's, where Western blots as well as other assays are used to determine if the HIF-1A concentration within the tumor. Based on the amount of concentration of HIF-1A will help the physician understand the malignancy of the tumor. In regards to patient prognosis, identification of HIF-1A protein overexpressed is a sign of malignant tumors and can be seen in cancer tumors such as colon, gastric, lung, skin, and ovarian. Due to the tumors being malignant, this is also a poor prognosis for the patient's survival. While if there is little or no expression of HIF-1A, then it's possible to think that the tumor is benign. And just a disclaimer that this is not the only way to identify the malignancy of a tumor, nor is it solely used to identify the malignancy of a tumor. So, today we presented different aspects of the enzyme hypoxia-inducible factor 1 alpha. We first showed HIF-1A on the protein level in regards to the different domains it's composed of and how it's related to its family of proteins. This information helps understand how HIF-1A is able to function in normoxic versus hypoxic conditions, and also the role that HIF-1A has in cancer cells. We then presented information on different research articles and how HIF-1A is an important factor in tumor growth and cell proliferation. Then proposed reasoning behind the data presented and showed how HIF-1A can be used to identify cancer malignancy and possible prognosis. Future research with hypoxia-inducible factor 1A can be very important for potential cancer treatment. Research is being done to determine if giving tumors more oxygen will reduce the survival of cancer cells and facilitate treatment plans. When cancer cells are deprived of oxygen, which sends HIF-1A in the cells and promotes transcription, giving the cancer cells a survival advantage. The future research is looking into giving the hypoxic tumors more oxygen so that less HIF-1A will enter the cancer cell, and so that treatments such as chemotherapy are able to attack the cells more efficiently. This happens because the cancer is not on high alert, meaning that it will not suppress the immune responses such as your CTLs and inflammation. So combining these two treatments has the potential to be a successful chemotherapy option. While cancer researchers are also trying to find chemicals that will either block transcription of HIF-1A mRNA or find chemicals that will bind, such as the PhD to the HIF-1A enzyme and help with the degradation of it. In saying all of this, researchers are understanding more and more about how HIF-1A affects the survival of cancer cells, and maybe one day you all can look back on this presentation and realize that this research was the platform for a breakthrough in cancer research. Thanks for listening.